Can you hear me, everybody? Can you hear me? You are. All right. Reply in chat. Hello, hello, hello.
Good morning.
My microphone says you can hear me, but I don't. Yay. Thank you, Ragad. Oh, sorry, I used your name. Thank you, everybody. All right, here we are. We have our activity from last week where we have a molecule with the formula C6H10O2, and it readily reacts with bromine. You don't have to copy any of this down. In carbon tetrachloride, and the molecule also has an intense infrared absorption near 1706 reciprocal centimeters. And then we're supposed to use this information up here and the following proton NMR data to predict the structure of the molecule. So remember, we're always given 3 pieces of information for proton NMR data, and I will interpret it as follows. 1, where is the peak? That's how many ppms. Reminder, you have to use the chart. I don't have the chart handy. I could get it handy. I will. And 2, what pattern is the peak? That's what multiplicity means. Is it a singlet, a doublet, a triplet? That's what this one is. And then the easy question, how many H's are of this type called A? Here it's 3. Ladies and gentlemen, looking ahead, when you see 3 H's of the same type, you should be thinking about a CH3 group. Yeah, I know it seems too simple to even mention, right? But let's start with these 2 questions down here, because these are helpful tips here, little extra information beyond this. Really, you should be able to solve the problem with only this information. That's okay, we have more. Things that react with bromine in carbon tetrachloride, which means bromine, which is Br2, in carbon tetrachloride, which is CCl4, that's a solvent. Bromine is a electrophile that reacts readily with. Bromine is, oh wow, typing's going to be fun today. Bromine is an electrophile that reacts, I know it's off screen, I'll fix that, with alkenes and / or alkynes. Jeez, alkynes. I don't know if I can fix it because my picture's in the way here. Yeah, there we go. There. Get that off screen a little bit. There we go. So there's the answer to the question. So you're told you have an alkene or an alkyne. Okay. An electrophile that reacts with alkenes or alkynes. What does an intense infrared absorption near 1706 centimeters minus 1 reciprocal centimeters mean? This is infrared spectroscopy information, which we're not going to cover in this course. But there's one fact I want you to know. This is the only fact I'm ever going to tell you. If you see infrared data, This just means a carbonyl is present. That's a very useful piece of information. Okay, carbonyls absorb that amount of energy in the infrared spectrum. There's no right process for solving these problems. These problems take extra time. They're a puzzle. This will take the most time of any question on the test, probably, except for part 2, which is the roadmap. I would set aside a half hour on test day for just this problem. Maybe do it early, or get everything you can done and leave a half hour at the end, and then just try to nail some partial credit on this, because it's easy to get partial credit, and give yourself a big pat on the back if you get the full thing. Okay, so I like to start with the index of hydrogen deficiency. You might not remember that from chapter 5, but it does tell us how many pi bonds are present, or rings. It tells us the total of those things, which can narrow down the information, because we know already this molecule has an IHD of at least 2. Do you know how I know that? Bromine is going to react with an alkene, which has a pi bond that gives an IHD of 1. A carbonyl has a pi bond that gives an IHD of 1. So you've got an IHD of 2 at a bare minimum. So if I do the work and figure out IHD and the answer is just 2, then I don't have to worry about rings. Nice to not worry about rings. So how do you do IHD? You have to convert this formula to a formula that has just C's and H's. So oxygen we ignore in an IHD. IHD, oh, I got my caps lock on. Corrected formula. Has nothing to do with question 2, so don't believe that it any relation to question 2. So this just becomes C6H10. I'm ignoring oxygen. The saturated acyclic, that means no pi, no rings, has a formula of C6H 2 times 6 plus 2. The only formula you ever memorized. C6H 2 times 6 plus 2. And wow, that's 1214. Wow, that's exactly what I said earlier. If you have an IHD of 2, here's IHD. IHD equals 14 minus 10, all divided by 2 when you're done, which gives, remember, it's pairs of hydrogens. That's why I divided by 2. Each pair of hydrogens gives an IHD of 1. So the answer is 2. Should put an equal sign in front of that. Useful information. I don't know what that means. Okay. Made everything bold. Z. Okay. All right. So we're only looking for a pi. Can't be an alkyne. We already ruled out alkyne. Alkyne by itself has an IHD of 2. Couldn't have a carbonyl as well. So now we know it's an alkene. Therefore, alkene and carbonyl. As soon as I figure out I've got a carbonyl, I always look for alpha hydrogens. If you forgot, alpha hydrogens are the carbon on the hydrogens on a carbon, one away from the carbonyl, and therefore has an E in the end. Sorry about that. Okay, so alpha hydrogens are hydrogens on a carbon, one away from the carbonyl. And if you look at your table with the ppms on it, the bottom left of the first table says between 2.2 and 2.6 would be where you find alpha hydrogens to a carbonyl. Do you have any peaks here between 2.2 and 2.6? Answer, yes. They're called B. There's 2 of them. Wow. Oh, that's a lot of information we got just there from this one fact. We know already that we have a carbonyl. That's a very big carbonyl. We have a carbonyl with a alpha carbon. A alpha carbon that has 2 H's. This is alpha. So here we go. And you don't get any points for this, but you're about to get 2 points if you can tell me what's next door to this alpha carbon, other than the carbonyl to the left. And the reason I know there's a CH3 attached is quite simple, because this pattern for peak B, you'd have to put a label on your test and say, I know this is B. You don't have to colorize it. It's a quartet. It has 3 neighbors. That's what quartet means. And n plus 1 equals 4. Therefore, neighbors is 3. So you're going to get multiple points very soon by just doing this. Tell me you know there's a CH3 here, and figure out what letter you're going to put with that. We already figured out B. We've got 2 points for B right now because everything here fits everything here. Now, the CH3 is pretty obvious. Which type of H is the CH3, everybody? It's called A. There's the only 3 H's on here. So this is going to be called A. You already have 4 points out of 10. Not bad. Okay. So we got to figure out other parts of this molecule. We haven't even talked about the alkene. Let's talk about the alkene. 1, are there any H's attached to my alkene? Those are called vinyl. Vinyl, V-I-N-Y-L. Those peaks, I don't have my table handy, but you do. The peaks are around, they're over 5. I know that. They're around 5. I've memorized that, but you have the table, you know the exact numbers. Let's make sure. I forgot to warn you today. This laptop in this location has been kicking me off the internet repeatedly. I'm surprised that hasn't happened yet. So if that happens, I'll just rejoin Zoom, sorry. So where are we at? We have to figure out our alkene. So I know already that my alkene has 1 H on it. How do I know my alkene has 1 H on it? Well, I'm looking at E up there in the table. There's 1 H on the alkene because that's the 5.5. Okay? Now, if you look a little more carefully at your table, there's it doesn't say this, but it's called a terminal alkene. And a terminal alkene is an alkene at the end of a chain. And I know there's a good chance this molecule has a terminal alkene because of this information for D. If you look on your table, terminal alkenes are a little closer to 5 right on the button. And there's 2 of them here. More information, this could be a terminal alkene. Wow. And everything fits that I put for D here. 4.9 for a terminal alkene, doublet for the 1 neighbor called E. This is the E. Okay. Don't forget to save. You don't have to be writing anything down. I want to repeat what's at the top of the screen here. If you could have gone without writing a single thing all this time, if it makes you learn better while writing, you know yourself better than I do, then feel free to write down. There's no penalty. I'm just trying to make you think as we go through this process. All right, let's finish up with E, because we don't quite have 4 points here. Sorry, yeah, 4. We have 2 for D. I can't give you anything for E because you haven't made all of this correct yet. You've made this correct, the first T up here, and I never talked about what the heck this means. I'm going to talk about it now. You ready? This, if you see it on the test, do not freak out. You should have a happy face. I'm giving you more information than I have to. NMR machines, the more expensive ones, will tell you more information. And we'll pretend we have state-of-the-art NMR machine. And these machines cost more than $1 million. I'm serious. What this information says here, on one side of the E hydrogen, which is this one, there are 2 neighbors. Sorry, I can't do that. There are 2 neighbors. Remember, 2 neighbors causes a triplet. 2 + 1 = T, 3. Okay, well, we've got that covered. The 2 neighbors are called D. Okay, now we're also told on another side of another neighboring carbon has 2 more neighbors. So wow, we're gonna be almost done after this, everybody. That's CG, CH2, 2 more neighbors. That would cause a triplet. And a brief description of why we just didn't add up the 4 neighbors for E. Do you agree there's 4 neighbors for E right now with the drawing? There's 2 over here on the vicinal carbon and 2 more on this vicinal carbon. That's 4 neighbors. If we didn't have an expensive machine, I would have written P here. P for pentet, meaning 4 neighbors, but I didn't give you a lot of information there. I gave you more information here. I broke down the neighbors. Okay, so we're almost done. Like I said, these 2 neighbors over here would make a triplet for E. So as of now, on this 10-point question, yes, you get 2 points for each of these. 1 point for drawing it properly, 1 point for telling me you know this is A, B, C, E, and D. So you're at 8 points out of 10. Wow, I like it. A, B, D, E. Might be, is it more than 10? No, 10. Now, what do you call these H's here? They are on a carbon, 1 away from an alkene. We call that allylic. Do we have any peaks that are called allylic in my table? And the answer is yes. We have peaks called, let's see, or maybe we don't. Maybe we don't. 2.3 we covered already. That could have been allylic. That's why I got excited. But then I realized we came up with something reasonable for B already. It was over here, and that's not allylic. Yes, there's overlap in our categories. Life is not, what do you call it? Cookie cutter. So apparently we don't have allylic, or something happened to raise this peak above allylic, and that's what happened. We're going to be talking about these hydrogens here being in 2 categories eventually, and we're going to make this thing fit. If you look, the only thing we haven't talked about is C. We've covered A, B, D, and E. C is at 4.4. And I'm going to make a small apology, but it's going to be a very useful apology very soon. I didn't realize when I was inventing this question that C actually fit in two categories. Whoa, that was a dangerous little erase, wasn't it? I need some white out. We're going to be editing this. Oh, that's a big dot. The good news about a chem draw lecture, which is what I'll call this, is that it goes slow for you. You like slow. We're going to be editing that number. It doesn't work. That number would work for if there was an oxygen here attached to this carbonyl. I'm just going to cut to the chase, as they say. I'm going to grab this. We're going to bring the whole thing together. What happens if I flip this? Does it look terrible? Does not. Quite happy. All right. Now, first of all, I know for this to be C, it needs to have two H's. Hey, check, two H's. Good. It's going to be C when I'm done. I've done all the C's, H's, and O's except for the second O. I need a second O is the only element that's missing out of C6H10O2. I've got my 10 H's. 3, 5, 6, 7, 8, 10. No more H's. I've got all my carbons. 6. 1, 2, 3, 4, 5, 6. The only thing missing is an O. So the only thing that this can be right now is if this O is connected to that. Oh, sorry, I moved my C there. This is the molecule. I just had a bad number for you, which is an opportunity. And I've decided that this activity has got a lot going on. So reward yourself. We're going to have 3 activity points for this one activity because there's been a lot. And I'm going to take a few minutes to talk about why C fits in 2 categories and why the number that I had originally, I forgot what it was. I think it was close to 4.4 that I erased, is inappropriate here. If C was just like this and there was nothing extra here, the 4.4 would work. Please verify that for yourself. This is a C that's part of an ester attached to the O. You need to go to your table with the ppms on it. Look at the top right entries. There's 2 of them that kind of fit this, with this being a better fit because there's 2 C's and not 3. And I believe 4.4 is right in the middle of that range. So it would have worked if there was no alkene over here attached to C, making it allylic. So this would be 4.4 ppm. Would be a good number for that C. Now, what would be a good number for this C? If this was the only thing going on for C, what would be a good thing for that C? Well, it's straight up allylic. I believe the range is 1.6 to 2.6. I'm going to the chat right now to see if you have a correction for me. It has allylic written on your table. It's not a hard question to answer. So when I said 1.6 to 2.6, was that correct? Or please in the chat, tell me what the real range is. I will wait 5 seconds. Is it 1.6 to 2.6 for an allylic H? Somebody said yes, thank you. I hope I can just clear that without getting rid of people. Good. What's in the middle of 1.6 to 2.6? Well, I'd say 2.1. So there's the 2 categories and their numbers. when a molecule has H's in two categories, there is what we call an additive effect of each category. So what you need to do now is figure out what this would be, which would be a CH2 that has nothing special going on. We call that a baseline. Nothing special, no other categories and no single categories except that it's an alkane with two R's on it. So my baseline, and I believe the fit on the table is 1.2 to 1.4 here. I'm going to go to chat and see if 1.2 to 1.4 is correct. Somebody could just type in yes, or give me the real range here. Good practice for you. On the table, I think it's the fourth entry. RCH2R. Yes. 1.2 to 1.4. I don't have time information here. I think somebody just said yes. So in the middle of 1.2 to 1.4 is 1.3. Oh, it's not typing. Please type. Okay. So what was the effect? This argument's going sideways now. There's two things going on. Two things. Baseline, I wanted the curved arrow. Goes up to 4.4 is one category. And the other one is baseline going to 2.1. That's the allylic category. The top one was the alpha category. So what's the jump going from 1.3 to 4.4? That's a jump of plus 3.1. That's the difference. What's the jump of going from 1.3 to 2.1? That's a 0.8. Combined jump is 3.9. Nothing hard going on here. So now, if you had to predict a better number, we're going to correct my question now. A better number would be baseline plus 3.9. So starting here, nothing special. The two combined, 3.9. Overall, a better number is 5.2. We're going to copy that over the box. Save. We're going to put it in the box. You won't see it. Very rare you get to use a white here. It's hard to make things white. I've done this many times. It doesn't save properly. Yeah, you can see it there, but when I save this, it goes to black again. I don't know why. I'll put 5.2 down there as well. That one we'll be able to read if it turns black. So I should have had that number there instead. And all you need to copy right now is what I put in this box. Just copy that. And what's going to happen is you just put your name. I don't need any other information other than your name and what's in this box. And then you take a picture and you go to Moodle and you go to the bottom of Moodle. There's a new area there and it's pretty self-explanatory. This is activity 1. So I'm gonna just look at chats because I need to know when the first person submits. I need to know if it worked. Just say it worked. And then we'll come back at 8:45 or 8:48. Give you lots of time because this, it's a new deal. So you have until 8:48 to submit your name and what's in the box. I will put that in the chat right now. If I can find the chat. I closed it and it disappeared. I think I would have to stop the share to do that, and I know. So I'll just put it here, outside the box. Activity 1, before 8:48. Bam. Any format you want. JPEG, so you can just take a picture and upload the picture. You don't even have to use Cam scanner or whatever. Okay, I'll be back. I can't look at the chats. If you feel brave enough to just say, I just need to know, somebody just needs to get on video and say, it didn't work. Otherwise, I don't need to hear anything. If it didn't work, I got to fix it. I'm getting my coffee.
Dr. Whitaker, I submitted it. But it says that it's late by 10 minutes.
I will be posting all of these in a lecture document after class is over.
Professor?
Yes, I may have answered your question already.
No, you haven't. Why are we? Oh no, why are we doing Zoom today?
It's personal. I really can't talk about it. I'll just tell you it's not COVID related. I can tell you that. No, not a
Okay.
COVID issue. All right.
Okay.
Yeah, we'll be starting our next segment in 3 minutes. I'm just checking on my phone to see if everything's copacetic here.
Do you want us to leave the Zoom?
No, you can hang in there.
Oh, okay.
Or you can leave. We're good as long as you're back at 8:48. It does take a long time to get to the bottom of Moodle on a phone. Here we go. I see we already have 11 submissions. That's good. That might be everybody that's here. Yeah, I left a buffer until 8:55, but you just get it done by 8:48. We're cool. And my apologies. I just noticed I had my computer on mute. So if anybody was saying anything, that's why I didn't respond. I didn't hear anything. But I turned that off. If you speak now, I hear you, obviously. All right, just enough time to put another coffee on. Okay, everybody, we're back. We're going to do activity 2. So it's going to disappear. And activity 2, and I made it so nobody is going to feel rushed today. So if you want, you can copy as I write down the question, and I don't know if you have to, but it's a mechanism, so you're going to need to draw molecules. So give a mechanism. There'll be 2 simple reactions here. This is chapter 15, by the way. Hello. Give a mechanism for this reaction, and these are going to be big molecules. All right. So there's a ketone. When we get to chapter 16, you won't be surprised that's called cyclopentanone. And we're going to react this thing with 2 reagents in sequence. So it's really 2 reactions. One, we're going to react it with, I'm drawing it here, but I'm going to move it up there, okay? And this one will be MgBr. We've never seen magnesium in this course. MgBr attached to, I guess you'd call it an isopropyl group, right? Won't be surprised the name is isopropyl. Magnesium. bromide, which implies the bromide's an anion, and so is the carbon, and that's your normal oxidation state for magnesium. It's a 2+ ion with the 2 minuses to balance it, being the carbon and the bromide. And then 2, simple acid-base reaction. HCl, cheapest strong acid we've got. Actually, sulfuric acid's a little cheaper, but let's not worry about cheap and expensive. And this is pretty exciting stuff, people. This is the easiest way to do synthesis that we've seen. I want to remind you, we did synthesis with alkynes before, but those are some pretty nasty conditions to make an anion out of an alkyne. And here we go. Want to make it look pretty. Why is it exciting? Because you have a new carbon-carbon bond. It's called synthesis. Still haven't lost the internet once. Wow. I guess using Zoom makes my internet connection more stable. So that'll be one of the reactions today. In fact, I think we'll just make this activity 2. And we're going to do another mechanism in activity 3 that's a review mechanism. And it's going to look a little like this one. So we got that. And in chapter 15, we're going to learn this is called, I don't know, we're going to have a little box area out here. There we go. Little box area where we can put notes. Starting up here. This guy here is almost the same as, we got a symbol for almost the same as, a big old double bond here. Well, big. Then we need this character on our keyboard. I don't know, about a 55-point font. That means almost the same as, I'll put that over here. Almost the same as an anion on this carbon and a cation here. That's kind of like ignoring a spectator, isn't it? Except it's a weird spectator. There's your cation, here's your anion. So you can start your mechanism with the anion, but make sure you put a lone pair on it. And horizontal didn't do it. There you go. So I'm just going to move the anion down here. I didn't change it. And I'm going to make sure I have a lone pair, else you're not showing me what pair of electrons it's going to be using. I don't need 2 lone pairs. Save. Oh, I was silly. I have to save 2 versions. File save as, because I want to post a blank, right? There we go. I'll post the unmechanized version and then this one. So if I want to do a mechanism now, turn that off. Back to this. Curved arrows using ChemDraw is a real nice way to learn mechanisms, but it's real slow. There's my curved arrow. I don't want it ending here. I don't want it ending there. I don't want it ending here. I want to end at the carbonyl. You know why that's attracted to the carbonyl? I sure hope you do. Negative only likes one thing, positive. Carbonyl. Carbon is very positive. Not a whole 100% positive, but quite a bit positive. That's the Greek letter D, lowercase. Oh, we got that. And the oxygen, because it's more electronegative, is not delta positive, minus. And you can't have 5 bonds to carbon I want to make sure that's clearly attacking there. All right. This breaks. This arrow starts on the pi, ends up on the O is a lone pair. We're almost finished this mechanism. That's how easy it is. So we're going to do reaction arrow here. Leads to something that looks almost like this, except the O doesn't have an H on it yet. The O is an O. It's got 3 lone pairs, but we only need 1 of them for later. I've got a lone pair. I don't have to draw it again. Be about 90 degrees off there, and it's an O that got the electrons it was tugging on. And now it's got the real minus charge. It's an oxide ion, the conjugate base of what? Conjugate base of an alcohol. Hey, look at that. The alcohol is the final product. How do we get there? HCl. Simple acid-base reaction. Lone pair attacks H. Sigma becomes a lone pair. I'm going to colorize my arrows, and that's it. We got a little more writing on this one. Not much. And then let's see, right now 8:57, 10 minutes. Submit before 9:07. Just everything to the left here. Submit before 9:07 a.m. And that's going to be activity 3, 4. What? Remember, the first activity counted as 3. This would be activity 4. I don't know. If I put it up there, it's going to freak some students out. It's really the second thing we're doing, so I'll leave that. All right. I'll see you at 9:07. I'm going to check on my phone to see if I'm remotely close to 9:07 on the submission for activity 2. So I'll be back. I'm gonna put some stuff over here that you don't need to worry about for our next activity, which will be starting in 4 minutes.
Professor, so all of this is going to be in one recording or one video?
One video and one document. Yeah, it'll be. I'll post a document in our normal lecture area with one video.
Okay.
Yeah. All right. So on the right, if we're looking ahead on the right, probably everybody's probably done. We looked at in our example just to the left there, we did a Grignard reagent reacting with ketone in this case. And we could have used an organolithium reagent instead. They do exactly the same things. So whenever you see carbon, magnesium, halogen, that would be the same as carbon, lithium. They're both C minuses. And we're going to use the lithium on our next example. It won't be a ketone though. Isopropyl lithium here. Easy to name these things, huh? A little backwards. If you're looking at it, they named the anion first and then the cation. That's a contrary to the rules of chemistry, right? And then we're gonna have, instead of this guy, oh man, I'm getting greedy. I was trying to save myself from redoing the mechanism. No, that's not how you help students learn. There you go. Yeah. We'll have we'll do 1-methyl, cyclopent, 1-ene oxide. Some of you might know what that means. This will not be the product here. Don't know when that's going to be. So you draw a cyclopent, but don't draw the ene. Do not draw the ene. So down here I'm drawing it. There's your methyl on 1. The oxide means where there used to be a double bond between 1 and 2 is an epoxide. Triangle, not a triangle like that. Triangle with an O in this corner. Right there. And what we're gonna get when we're done, an OH there, and probably not a surprise to many people, new bond on the less hindered carbon of the epoxide, that should strike a familiar tune for most of you, for all of you, I hope. This is a nucleophilic opening of an epoxide. It's not new except for our new what? Our new nucleophile. Hey, new. I'm gonna write that down. I like it. New. And we're starting. C minus. I think you could probably, hey, I'm going to give you 2 minutes to do the mechanism on your own. I bet most of you can do that, but you don't, hey, if you're stuck, we're going to go through it together. But I think you know which carbon to attack with that lone pair. It's got a red bond to it in the product. I think you know which bond to break after you attack that carbon. It's this bond. And you're going to get an O minus after the arrow here. It looks just like this one because you don't break this bond. It'd be an O minus up here. You put that down here. HCl, we're going to need it again. So let's put it over the arrow. I'll put it under the arrow because where's my O? It's under the arrow. There we go. This is going to be easy speasy. Watch this. We're almost done. We don't have OH. Here's the beauty. One of the beauties of ChemDraw. If I just tell them it's a minus here, it'll get rid of the H for me. ChemDraw, sometimes smart. Sometimes it thinks it's smart, and it's not. Need a lone pair. There we go. So review mechanism. Right there. Curly. Cl minus. Colorize those arrows. Oh, we never did our first arrow. Oh my goodness. First 2 arrows. Same as the previous example, except we're not. I think going to the left would be a little better here. Yeah. Right to that carbon there. O gets a lone pair there. Boy, I didn't hit the O. Yeah. Colorize that. Okay. So there we have it. We have an organolithium. This could have been a Grignard again if you wanted. Could have had the old MGBR up here. It doesn't change a thing. And when do we want to submit this by? Submit by 10 minutes from 9:10. No, it's not going to take 10 minutes. Most of you have been doing it within 2 minutes. We got away with 9:15.
Is this considered activity 3 or still 2?
Oh yeah, I didn't edit that. Yeah, I need my editors working with me here. Yeah, thank you.
No problem.
Yeah. I'm gonna save it over activity 3. I just erased activity 2 key, didn't I? Oh boy. I'm giving myself a little more work, aren't I? I'm gonna have to redo those. The first one. Not a lot of work though. Looking ahead, let's make sure that doesn't happen again, huh? Okay. Add one more comment over here. Grignard reagents are always intermediate interchangeable with organolithium reagents. Gotta cover myself here in Chem 242. So you'll never see an exception to that. In Chem 242.
Oh, are we doing another activity?
Or there are lots. Well, not a lot.
Okay,
We'll keep going all the way until 10 o'clock.
that's perfect.
Professor, there's only three slots to submit. Are you gonna add like more slots for the rest of the activities?
Yeah, they're going to appear later. Yes.
Oh, okay.
Also, Professor, I have another question. It's like
Sure.
about the practice exam. Are you
Yes, sir.
are you willing this weekend if I have any questions to answer them for the practice exam so we can get ready?
Oh, of course.
Okay. Yep.
Yeah.
I just didn't want to ask you too soon about it, that's why.
Anytime, just email me. No, go ahead. And yeah, that's actually really good if you can get early requests in, because that gives us good starting points for activities. And I'll answer your question always within 24 hours. I try. And then we'll do it together in class if it looks like a good activity.
Okay.
All right, we got 9:15. I'm gonna edit this to be activity 4. So actually, I want to add one more comment here. It's not part of the quiz, so just keep adding comments. I don't know, maybe I'll make this smaller. Then the comment box to the left here. Fixed it. No, not fixed angles. For epoxides only, a Gilman reagent, which you don't know what that is yet, also does the same reaction. And here's I got an idea. See the next activity for the identity of a Gilman reagent. Of course, pictures now in the way. There we go. Next activity won't be a mechanism, it'll be how to make all these things. Grignards, organolithiums, and Gilmans, which we don't even know what they are yet. So that's going to be activity 4. So we got the right name. I think I should save that. I'll be very careful this time. Yeah, it's going to ask me, do I want to replace it? Answer's yes. And then we're going to go with 4. Don't write anything down until I say it's okay. It'll be activity 4. Hey, editors out there, please help me if I forget to change something. Synthesis of Grignard / organolithium / Gilman reagents. So get rid of everything underneath here. Don't know what time we're going to be submitting, but I know I'll need that comment. Here we go. So we always like to start with alcohols because we have all the alcohols in our storage room. I mean, seriously, we have all the alcohols in our storage room. And that's just 2-propanol. And you are copying everything this time, so you might as well start writing. 2-propanol, also known as isopropanol. And a lot of you know that's also called what in your medicine cabinet? Anybody? In your medicine cabinet right now. The one you would put on a wound. All right, here it is. Rubbing alcohol. There. Okay. For every single one of these reagents, I got rid of the title. I had the title. Where? Oh no, I had a nice title, and I got rid of it, didn't I? You think it's still on the old activity 3 key? We'll find out. Nope.
It was on the bottom.
Oh well. I had a title up there, and I got rid of it when I.
You put it on the
around.
bottom, Professor.
I put it on the bottom. But I do have to get rid of that. Thanks for the reminders.
No problem.
And instead of this title, synthesis, I just didn't have it saved. Synthesis. So of all these things, Grignard / organolithium. Gilman reagents. Okay, so every example here, we need to make it into an organic halide first. Could have been bromine, could have been chlorine, could have been bromine, chlorine, any of them. Iodine, except we don't know that reaction. Back on. So PBr3 is a very reliable way of making an organic bromide. Start that up here. We could have used the chlorine version. There. Now to do, there's no PCl3. Some of you may know PCl5 works. Why are you doing that? Sorry. But the one we learned, and you should always be reviewing, SOCl2, and what's its partner in crime almost always? Anybody? What do you always see with SOCl2? It's okay, we're shy today. That's fine. Pyridine. You don't have to answer any of my questions today, it's fine. And that will give us a Cl, and a PBr3 one would give us a Br. Two reactions that have just became even more important. You already knew they were important. Every reaction in chapter 10 is important. But now we're learning another reason why they're important. They get us towards these Grignards, organolithiums, and Gilman. You can take either one of those. So where's my parentheses? Got a nice parenthesis right there. Let's start here and go down now. Let's start from the bottom. Doesn't matter which one. You're going to react it with, let's see, let's do it this way. We're going to cover the first two things right here. That's going to be an arrow going to here, and then a different arrow going here. Be a nice little summary here. We can make the organolithium there. Make the Grignard here. You react it with elemental lithium. Elemental lithium. In a very, the least polar solvent you can think of, hexane. So it doesn't matter which of these two you start with. You get, well, I already have it drawn. This one. Yeah, this one I'm going to change to MgX. Here, X equals Br or Cl. Br for the top stream, Cl for the bottom stream, doesn't matter. Those are going to be, they're just on the magnesium there. And you have just learned, well, you haven't quite learned how to make a Grignard. And the organolithium here. I think we don't have to have the same notes on every document. I need that area. This whole document's notes. There you go. This comment's worth repeating. Notice I didn't include Gilman's on that. Gilman's are only interchangeable if the reaction that's next is with an epoxide. Okay. Another parenthesis. Yes, go ahead.
What are the reagents for the Grignard reagent?
Oh yeah, I
Is it just
said I
magnesium?
didn't give it to you, and I'm continuing to not give it to you. I'm teasing you. Thank you for paying attention. Magnesium metal. This is not normal magnesium. Magnesium metal, and here you can't just use hexane. You would get no reaction. This is a much pickier reaction. You need a solvent that's still non-polar. That's going to be shrunk down. But you need to have an oxygen in there with a lone pair. That's oxygen always has lone pair. That solvent there is the cheap version that you can use here. That's diethyl ether, isn't it? Ethers are, you know, even if you don't know nomenclature, I mean, that's pretty self-explanatory right there, the nomenclature, isn't it? And if you read the book, it talks about why you need the lone pairs on that solvent, and you don't want to have a solvent that's got a proton attached to O, because these guys, not only are they do things with ketones and aldehydes, but they also are very strong bases. They're the strongest bases you can think of. They're the conjugate bases of alkanes. So that's the strongest base possible in this course. So you can't have protons in your solvent. You'd be making the reagent and destroying it immediately in an acid-base reaction. You'd be making propane, most expensive propane ever. All right, so you know how to make an organolithium. In summary, how do you make an organolithium? You take an alcohol and make it into an alkyl halide, either a bromine or a chlorine. And then you react that product with lithium and hexane, and you will get an organolithium regardless of which of these two you started with. Similarly, how do you make a Grignard reagent? You start with an alcohol. You can make either of these two, and then react it with magnesium metal in diethyl ether, and you make a Grignard reagent. Now, a Gilman reagent has copper in it. So move this a little here, and we need a copper reagent. And it has to be copper plus 1, not copper metal. Copper plus 1. In fact, it's very picky. It has to be copper plus 1 with an iodide. So nomenclature, Chem 141, copper, Roman numeral I, iodide. And what happens there is you're gonna make, gonna look interesting. You're gonna make this, but not, you're not done. See you. And it's gonna have another one of these underneath. Where are you? Anyway, it's got 2 of those. So it's got stoichiometry here. You need 2 of these to make this, or 2 of these to make this. Don't in your mind say, oh my God, we got to make one of these and one of these and combine them. No, that's not what this means. You can take either one of these and use, let's see, I'm gonna be very clear, I hope. If you made 1 mole of this or 1 mole of this, you would only need a half mole of this. No, that's not a 0. To make a half mole of this. And it's got an anion on the copper. It's called a, well, I don't know, a rhetorical question you don't have to answer, but there's a name for molecules that have a transition metal in the middle and what we call ligands attached to it, to more than one. Ligand is just a group attached to a transition metal, and they're called complex ions. You don't have to know that, but that's what these are. And some of you will remember when Dr. Yackel, Dr. Buchanan, or whoever you had for 141 talked about complex ions. And I guess we have to put something over here for a cation. You get the symbol for the cation. Call it Y with a plus. And Y equals, very simply, if you went with the top stream, Li plus, or if you went with the bottom stream, hello, or MgX plus. I put the plus first, MgX. Why do you keep doing that? Sorry, talking to my computer, not you. There. And those are spectators. I don't need to see them anyway. Another way to write the molecule would be R2, 2, 2, CuY. That is a Gilman reagent. And that's the end of this activity. It's a bit by 9, hopefully 9:38. And I will go off screen and make sure I've got that one set up. I don't have anything there yet, do I? So you go ahead and scan. I gotta set this up.
Professor? So
Yes, sir.
on the exams, do we have to know the mechanism for this, or is it going to be like a prediction?
No, there's a lot of interesting stuff here that is actually not fully understood to start with. So there's no mechanism for you to be responsible for, but I'll highlight the things you've got to know. You better know these reagents, of course, right? important stuff here. These guys in blue. You got to know those chemicals and what they reacted with. So I've got to do a new activity here. It's going to take a while on the phone, but that's okay. You guys aren't in a hurry, are you? Don't think so. All right. Oh, wow. What did I call the other ones? I can't even remember. We'll start with the date today, January 24, activity 4. You can just ignore me if you're busy. I won't put any comments this time. That. And we want up by 9:38. I already had 9:33. Now. And give you a little grace period, 9:42, 43, that 5-minute grace period in case trouble. All enabled, file submissions. And hopefully I got it. So it should be there now. No comments on it this time. Run to the gun, there's only 2 minutes and 54 seconds. Due date. Yeah. And I got a couple minutes to set up number 5. I think everybody's done their submissions. And see what we have here. What have we learned so far? We've learned that we have to save things properly. That's what I've learned. Well, I'm supposed to have learned that lesson decades ago. You know, life. And I'm going to be doing activity 5. And still chapter 15. We're going to be finishing 15 right now. It's a short chapter, and I'm distilling it down to the essentials. I think it might be time for a mini road map, huh? Okay. And I'll sneak in one new thing that we haven't done here. Let's do an aldehyde this time. Because really, the most important thing about chapter 15 is how it relates to reactions with aldehydes and ketones. That's the most important thing. We learned that epoxides are pretty important too. I missed. All right, here we go. This time an aldehyde. And you know, we should always remember how to make aldehydes too from alcohols. That's just standard review 101. We need a reagent box. Nice box. If you don't want to write everything down, you can just copy boxes and I'll label them so you know it's got a letter in it. You need to copy the box. Review reactions, we're always putting review mixed in with our new stuff. The whole purpose of this course is to bring it all together, isn't it? Okay, we can do lots of cool stuff with the aldehyde. We could do some new stuff. And let's see. Call this B. How can I make that into something like this? It has a new bond here, ethyl here. These molecules are taking up a little too much room. Don't redraw them. I'm making it so it takes up less room. That's all I'm doing here. Otherwise, buying myself some room on my page. This is my day making exams doing this, you know. All right. That was cool. Another review reaction down here. Oh, it's C. How can you make that into an alkene? It's a good review. Alkene, no OH. Because then we can review how to make that into an epoxide. Call it D. Dang, better ways this way. Gave me the arrow. Chem draw, like I said, thinks it's smart a lot of times. And epoxide right there. And you're gonna tell me how to make that into this thing where we keep this bond. Hello. Keep that bond. Make a new bond. And we just put a methyl on there. How's that? And have at it. Then we'll do my favorite stuff. One. Lithium. No, we can't do that. Lithium. PBr3. PBr3. 3, 2, lithium, hexane. Oh, what happened? Caps lock clearly beside the letter A. 3. We'll do formaldehyde. No. Why'd you do that? 4. 8. Hydrochloric acid. We'll have a big old product box at the end here. Sneak an arrow in right here. Product box. I don't know. Don't have room for a product box. Sure we have room. Watch this. Ha! Sorry. There should be a letter in that box. F. Okay. Okay. Change this up. Let's start from scratch. We're going to go with lithium. It's not lithium. SOCl2. SOCl2, comma. That is an acceptable short form for pyridine. You can use it on tests without asking. 2, magnesium. Magnesium in. Diethyl ether. Ether. What does that mean? In diethyl ether. That's just a fancy way of saying the solvent is diethyl ether. 3. I reacted with formaldehyde. Or I reacted with cyclohexanone. 4. Copy. Same 4. Paste. Gives us product G. Yeah, let's put an arrow like this. Roadmap construction. Almost over. And then the new thing I promised. Oh, got formula here. Nice. See, we did the bromide. We did the SOCl2. Pick one of them. No. Here's what we're gonna do. Here's what we're gonna do. You're gonna give me some reagents here to get from there to here. That would be H. I guess this is our last activity. I think I heard cheering. Nice. Okay. So how am I going to do this? I think I got it. You ready? I want you to make this reagent here. I'll be moving it to the arrow very soon. I have 2 groups. I have ethyl. Oh, how about this? I can do this way. Or sure. Et2CHCU. I didn't need the parentheses, sorry. Oh, I did. There's two of those attached to the copper. And in this case, we will have MgCl. And that's not the new thing. That's I'm saying, wow, it looks new to me. But that's not new compared to the stuff we've had already. This next one's the new thing. And this is a unique reaction to Gilman's, which is this thing here. That's a Gilman. And what I want to do is grab this guy. And it won't be NOH at all. Attached here. Put like, yeah, it takes up less space if I make it Z. Let's get Z. We got that. I'll try to help myself in the future here. Go like this. Don't call that key. I mean, the way I know. Sorry. Key back. All right. Ready? Drum roll for the big finish. How do we make alcohols where there's a C that has one bond to O into an aldehyde that has a C with two bonds to O? When you see that, if the word oxidation doesn't come to your mind, then you need to review oxidation. Increasing the number of bonds to oxygen, the carbon gets more and more positive, loses more and more electrons. Loss of electrons, oxidation. When you have alcohols undergoing oxidation, there's only one element that should be in your mind, and it's called chromium. Now, your choices of chromium are potassium dichromate in aqueous sulfuric acid. Bad choice. Makes carboxylic acids from primary alcohols. Next choice, chromium with 3 oxygens, CrO3, also known as chromium 6 oxide in aqueous sulfuric acid. Also bad choice, makes carboxylic acids. This is not a carboxylic acid. I hope you see that. Third choice, correct choice, pyridinium chlorochromate. You can write that in the box. But it's perfectly acceptable to write PCC in the box. Pyridinium chlorochromate makes primary alcohols into aldehydes. You will be using that reaction no less than 3 times on every exam until the end of the semester. If I disobey that statement even once, you by pointing that out to me, get an extra point on your exam. This is the only time this will be mentioned. Okay? You email me, say, I only saw PCC on this test twice, Dr. Whitaker. You hear that? Okay. That's how important it is. I'm trying to tell you. So we made an aldehyde. Hey, there's a new bond here. Are you excited about that? You should be, because that's called synthesis, making new carbon-carbon bonds. There's 2 ways to do this. And I better pick it up. I know here. Isn't that just an ethyl group up there that wasn't there before? We can call it ethyl. How about ethly? That will not give you the product drawn. That will give you an O-. Listen carefully. Every time you use an organolithium or a Grignard reagent, which would be ethyl magnesium bromide or ethyl magnesium chloride, you must follow it with hydrochloric acid to get the H onto the O. If you forget to put these numbers 1 and 2, you will lose a 1/4 point, which is much less damaging than losing your life in the lab, which is what would happen if you mixed ethyl lithium with HCl in an uncontrolled environment. We're talking about the strongest base you know, reacting with the strongest acid you know. The exothermic reaction will ignite the propane that you just made and create a fire that blows up in your face. Sorry, that was a little harsh. But in lecture, forget those two numbers, you lose a quarter point. Okay, now I've made an alcohol. I'll go through the conversions here in this box. Do not copy this box until I say copy this box. Step 1 converts the OH to a Br. Do not copy it. That's step 1 only. Step 2 converts the bromine to a lithium. Step 2 is done. Step 3, formaldehyde, which is the simplest aldehyde. 1 carbon gets attacked. And you get a CH2 attached to an O-. Do not copy that. It's only the result of step 3, where there'll be an O- right here. I'm going to put OH because step 4 converts O- to OH. There's your molecule. Fit it in the box. Moving on. Step 1 in this, we'll do the steps for you again. They'll look good on the video. SOCl2 and pyridine. Step 1 puts a Cl here. Oh, that's not the right molecule. Ah, sorry. Step 1 puts a Cl here. I know we're out of order here. Step 2 converts that to MgCl. Step 3, cyclohexanone gets attacked at the carbonyl. Cyclohexanone gets attacked at the carbonyl. Carbonyl becomes an O-. Step 4, you guessed it, O- becomes OH. That's a huge molecule. Still huge. That now fits in the box. All blue. Go blue. Oh, there, go blue. Go blue. I can't see. Okay. Yeah. We're running out of time. H2SO4 and heat. Yeah. All right. Heat. Capital D, convert to symbol font. Blue. Made an alkene. Acid catalyzed dehydration of alcohols. Chapter 10, I believe 10.5. Don't quote me. So you verify. Making epoxides. There's two ways. Because of time, I'm just gonna give you the simplest one. And it's acceptable to do this generic per acid. You don't have to give me an R. You are responsible for knowing 4 R's. Go to chapter 11 and look up the synthesis of epoxide for the nature of the 4 R groups, which may be 3 R groups, I'm not sure. Now you've made an epoxide that needs to be attacked by a methyl Grignard, methyl organolithium, or methyl Gilman. All 3 work. This is the only time all 3 work. This is the only time all 3 would work. You can't use Gilman's to do this reaction. You can't. They don't do it. Okay, so I need a methyl organolithium. I think the easiest way is to say not ethyl, but methyl or Grignard. And you've got that. I'm trying to get done in 3 minutes. You made your new bond. You attacked the less hindered carbon. This bond was never broken. It became O- and HCl made it OH. Now, I'm gonna pull a fast one here. On tests, I I typically like to remind you that it's not a one-step process to get from an alcohol to a Gilman. It's not even a two-step process. Wow. That's a three-pointer in that box. You look at that roadmap we just did. Step one was to convert this to a organic halide, like a bromine or a chlorine. So ignore this typing. I'm editing it. This will be the last step. I don't know what number it is. I believe it'll be 4, believe it or not. I need to make it into a bromide or a chloride. 2, you must make it into an organolithium. You must know organolithium solvents. It's not step 3 HCl. Step 3, some kind of copper. Running out of time. It has to be this copper. And it's step 4 HCl. You don't get a 4th point because that's just an afterthought reaction to convert your. Oh, we don't even need it. We made an organolithium. No, we don't need HCl. Sorry. I was thinking about aldehydes and ketones. These 3. Sorry if that was confusing. Yeah, sadly, only 1 minute for this reaction. It's called a coupling reaction. Unique to Gilman reagents. You cannot interchange anything here. I think that just gave you the answer. The cool thing is, I know you're thinking 1 too many carbons here, but that's not a carbon, it's a halogen. Could be Br, Cl, doesn't matter. Iodine works even better, but let's not worry about it. Blue. And notice the direction of the bond you make is the same as the direction of the halogen. This is not an SN2 reaction where it would be backside attack. No, it's a coupling. You keep the geometry of the alkene is all I'm trying to say. And it doesn't have to be an alkene. It could be an alkene or an alkane as long as there's a halogen there. That's the end. I might have to adjust the time on the submission because it's not right now. Okay, I'll be doing that. You're copying just the stuff in the boxes, people. If you haven't copied anything else, I need the boxes.
So the last box should be I. The one we just did.
Oh, because has to be I?
Should
Oh,
be,
I have the
because-
wrong letter. Thank you. I thought you were saying iodine. Yeah, I get you now. I get you. Yeah, I can't have 2 H's. That'd be terrible. There you go. Yeah, the danger of copy paste is you forget the edit. All right, this would be activity 5. I have an activity 5 yet or no? I can't remember.
This is the activity 5.
I mean, do I have a submission area yet?
Oh yeah, but the
I do, but I believe the time is wrong. Just have to change that. I'll make it 10:10. It's going to say the time is 9:50. I'm not changing that. I'm just changing the cutoff time. But it'll say it's late, but it's not. As long as you do it before 10:10, it's not late. And 10:10, you can't do it until 5, 4, 3, 2, now. And that's it for today, everybody. I'm hoping I see you in person on Wednesday. Very much so. Okay.
Dr. Whitaker, we have
That's it.
lab today, right?
You're showing up to, did you get my email about lab?
In J14 or something like
Yes.
that?
If you are my 244 students, you are showing up to room J14 at a normal lab time. Basement of old science building. Okay. And I think you're going to very much enjoy today's activity. Yeah, it won't be the full 4 hours, but it's going to be more than an hour. And,
should
that's
we
it
do
for
the
today, everybody.
should we do the
Yes.
pre-lab?
Oh, I'm going to
thing?
be I'm going to be setting up a submission area that you submit your bring your lab notebook, of
Okay.
course.
Okay.
I should remember to send this email to everybody with your experiment 16 set up in it. This is only for my Chem 244 students.
Okay. Thank you.
Okay.
Yep. See you at 12.
You're welcome. And thank you. All right.
Bye-bye.
I'm going to mute. No, I'll leave it on in case you want to talk. Big coffee day. Making more coffee, but if you say anything right now, I'll hear you.
Dr. Whitaker, for some reason, it won't let me submit activity 5 or activity 4. I don't know if it's my phone.
You might have been doing it while I was editing it.
Okay, I'll try again.
You've submitted the other ones or no? Yeah, I
Yeah,
think probably
yeah,
you were probably doing.
The other one's just fine. All of a sudden, my phone doesn't
Okay,
want to.
cool. Probably it took a little time for it to register my edit. Let me just see if other people have been okay with this. Oh, wow, we got more submissions this time. We had some, okay.
Dr. Whitaker?
Yeah.
I also had a problem submitting the first activity, but I emailed it to you because I tried again,
Okay.
but it wouldn't show me the button like to.
Yeah, it's because the grace period ended.
Yeah, I guess.
I don't know what to do about that. I'm going to edit activity 1 and make the grace periods like 3 minutes from now, but don't submit until I say anything. Okay. Cutoff is 10. I'll make it 10:08. And don't do it yet. So you should be able to submit activity 1 now. Just let me know if it doesn't work.
Yeah, it did work.
Yay.
Thank you, doctor.
You're welcome.
Enjoy the rest of your day.
Thank you. You too.
Thank you. Bye.
I'm going to sign off at 10:08, everybody.
Wait, Professor, I have a question.
10:10. Yes.
For like the first activity we did, I got really confused on how you knew there was an alkene.
How I knew there was an alkene. I'm gonna get rid of this screen, everybody. It's over, right? Everybody's cool with that? Activity 1. Oh gosh, doesn't even remember where I was. No, I gotta remember where I was. It was here. Where are you, activity 1? You're not here? Where are you? That's it. Okay, good. You got confused about how I knew it was an alkene? Because if it says it reacts with bromine and carbon tetrachloride, there are 2 possible meanings. One is it reacts with an alkene or an alkyne. There's the 2 things. Alkene or alkyne. And then I knew it was an alkene because I did the IHD. And I figured out the total IHD for this molecule was 2, which means at most there's 2 alkenes, but I know there can't be 2 alkenes because I was told with fact number 2 that there's a carbonyl present. That's a pi. There's a pi in a carbonyl. That's an IHD of 1 for a pi. You can't have two pies, which an alkyne would have, and a carbonyl. That would be an IHD of 3, wouldn't it? If you had an alkyne that has an IHD of 2 and a carbonyl, IHD of 1, the total would be 3. The formula would be C6H8O2.
Wait,
And that was not the right formula.
so how you figured it out is that you did this IHD and this is there's like 2 pi bonds?
I did 3 things to conclude there was an alkene present. The first thing I did narrowed it down to an alkene or an alkyne. That fact means alkene or alkyne. This fact means it's a carbonyl. The combination can't be more than 2 because this fact says that at most there's 2 pi bonds. Are we good now?
I think so, yeah.
Okay. I'm gonna move my 5-point tool here, just in case it's not clear when I save it, so you can read it. That dark gray. That won't show up in that background. That'd be nice. Okay. So I've got some work to do before I have the document available for you to look at. I will get busy on that right now. So everybody, I'm gonna go away unless you have another question. All
I'm
right.
just very confused about
Oh,
everything.
it's a brand new ball game. Yeah, I would expect everybody to be confused. I would be alarmed if you weren't confused. Sorry. A little harsh way to say it, but
Dr. Whitaker, I'm still having trouble sending the last 2. I'm gonna try doing it through my Yahoo instead of my Gmail because it's telling me my
the last 2, you mean 4 and
4 and 5. It's telling me that my Gmail is full.
oh,
So-
that's an issue beyond the scope. Yeah.
Yeah, so I don't know what's going on. So I'm gonna try to do it.
Do a screenshot of that message.
It
Can
won't
you
even let me
screenshot
know.
that message?
Yeah. Oh, that is telling me my Gmail's full.
Yeah, and
Okay.
use your Hawkmail. Well, that is your Gmail, isn't it? Any other email? I don't know.
I mean, that's what I said. I'm
Whatever
gonna
it
try
takes.
to do it on my Yahoo and see if I could send it that way.
Yeah, you have no deadline.
Okay.
You just
For
need
the
to
last
say
2.
what the technical issue was and attach both of them to the same one.
Okay, thank you.
Okay.
Okay, thanks.
All right, everybody. We're out of here.
Oh. Okay, bye, Professor.
Right, we're not out of here. We're back.
Okay.
Are we all out of
Bye.
here?
Have a good day, Professor.